First of all, some hints about your test. If you look at the ultimate review, I like number one. I like number one. Number one is a nice question. Number one is at angles. It's at right angles. In number one, I didn't actually even bother asking you to find the resultant momentum or the resultant velocity. I just said find the resultant angle, which is a way that I could ask you a question and not have you do as much work on a multiple choice kind of a question. I like number four. I like number four. But number four is free marks. Which of those expressions could be used to find change in momentum? Luke, can you get the headphone out of your ear if I'm talking? Thank you. Change in momentum. What's another word for change in momentum? Impulse. Which of these is the impulse equation? B. B. Okay, so that's kind of wishy-washy. Number five is an explosion in a straight line. Number five is a bit weird, though, because the initial momentum isn't zero. So your initial momentum is going to be this mass times 120 plus this mass times 120. Bang, they explode. And then I guess you have this mass times mystery velocity plus this mass times 140. And you can find the mystery velocity. So that's fair game, although I don't know if I'm going to put one quite like that on the test. What I'm really looking for is a good collision at angles. Let me look. Here, I like number 14, I like number 14, I like number 14. Number 14 is a nice question. You're absolutely going to have a collision at angles on the test. Okay? And that's a tough question, but it's what we've been practicing. I sort of like number 16, except in number 16, I'm asking you to find a mystery mass. I don't think I'm going to ask you to find a mass at an angle as written. If you can handle this, this is kind of a nice little advanced question. And there's good practice there because I think you will end up adding some stuff to detail. Although, since they give you both angles, it's not quite as bad as you might think if you look at my answer key. So I take that back. I don't like that one quite as much. I like something like number 18. What I mean by that is it's a linear question, but there's the idea of bounces back or rebounds. There will be a question at least once, maybe twice, maybe more than that, somewhere on your test where there's a change in direction, and you better let one way be positive and one way be negative. I like number 19. I like number 19. Although, if I give you number 19, I think I would add, instead of telling you the 8.5, I would have the cart start up here on a hill and make you calculate how fast it was going at the bottom of the hill, because that works in some nice energy. Wham, they collide. That's going to be momentum. And then how high up the next hill, that's some nice energy. There is going to be a using principles of physics right to explain question. I've glossed over a couple. I've dropped the hint somewhere, I think, during my lessons several times, so you should be okay on the using principles of physics right to explain question. But I won't tell you anything more than that. 21 is a nice conceptual one. In which case does it experience the greatest impulse? What's another word for impulse? Change in momentum. And since the mass isn't changing here, really the biggest impulse will be the biggest change in velocity, because it's mv final minus mv initial. I like number 22. I like number 22. This is an explosion, but my initial momentum isn't zero. I kind of take that back. If this was blowing up into three pieces, I think there is one later on. I'll show you in a second. I like number 24. I like number 24. Here's a rebound question again. Uh, 26 is good. East and north, so we have at angles. I like 26. I like 26. I like 28, because I see an east and a west. Again, a change in direction. If I'm going to give you a linear question about impulse or force, there's probably going to be a change in direction. I like 30, but again, 30, this to me is a little bit too easy. Probably I would initially, instead of giving you this 3 meters per second, I would have the cart starting up on a hill, and I would give you the height of the hill. So you'd have to figure out how fast it was going at the bottom of the hill. That would be part A. Part B would be wham, they collide, momentum. And then part C would be how high do they go up the next hill, change in height, change in speed, curvy path, conservation of energy. I like 31, I like 31, I like 31. Also, I notice a change in direction. So I would let one of these be negative, one of these be positive. Um, 34, I love 34. 34, there, that's a great example of a written question at an angle. Instead of asking you to find the final velocity, this time I'm asking you to find the initial velocity because they're sticking together, but that's perfectly fine. It's the same physics-y stuff. "37 is tricky but doable barely. 37, I want you to find the change in momentum, the impulse. I see south and I see an angle. I think you might actually end up having to subtract vectors. This is subtracting vectors at it's doable. It's maybe a little tough. You should know there will be a graph interpretation question, I think, on your test. Here, this is momentum versus time. The slope would be the force. Momentum over time would be the force. Okay? Again, I like number 7, but again here, I don't think I'd give you the 18. I think I'd probably have it coming down a hill initially because that just makes it more interesting to me, so you have to figure out that 18. 40, I'm not wild about. You could probably nuke 40. I stuck 40 on back when there was a provincial because this is an example of a perfectly elastic collision where you have identical masses and a 90-degree angle, and there was some good stuff for the provincial exam here, but nah. "44 is a nice example of graphing interpretation question. Here it's force versus time. The area underneath, I guess, is the impulse. How would I find the area underneath? I would probably break it up into a triangle, a big thin rectangle, and another triangle, and just base times height divided by 2, length times width, base times height divided by 2. Oh, that's a conceptual one that's kind of tricky. For this, I would probably make up reasonable numbers and just crunch the numbers and see what happens. "46 is pretty tough, but doable. I have one in mind that I'm looking for here. 47 is fine, I think. But it's got angles on your test. I'm going to give you a picture. There's no picture for number 47. There is a scholarship question that I like, though. I think. Let me go find it. Nah. Yeah, I said that. Not that one either. That one's cool, but tough. Sure, 51, this is totally fair game. I don't know why this was a scholarship question. This is an explosion. It's a slow explosion, but the life raft is stationary. It's got 2 passengers. This is like a bomb. It's a slow bomb, but the 2 passengers dive in different directions. The initial momentum of everything is 0. The final momentum of everything is 0. If you want a good example of an explosion that's not a boom, they explode question, but more of a slow motion one, this one here would be a good example. So I think this one is fair game. There is going to be an explosion of something that goes into 3 pieces on your test. Yeah, 52 is overkill. Not going to be that tough on your test. 53 is overkill. Okay, so there's some hints. Having said that, are there any questions, any types of questions you would like me to go over? If you can find an example from the review, that would be great, and I'll try and clone it and walk you through it. Questions from the homework as well are also fair game. What would you like me to go over? Someone needs to speak up because that works better. This one here? I'll change the numbers. I'll clone it. I know you hate that, but I want you to have the practice of doing the homework. Number 2. Here's how I'll change the numbers, Court. 1.6. There, now it's a whole new question. Some key things that I would underline either in real life or in my mind. That. What's this question asking me to find? So to find the kinetic energy lost, that's going to be how much kinetic energy we started with, take away how much kinetic energy we ended with. Before everything, what was moving? Before everything, what had kinetic energy? Well, I think this thing, because the other block was stationary. So if you want to know how much kinetic energy there was at the beginning, it's going to be 1/2 times 5.2 times 9.4 squared. Afterwards, it looks like we have 1/2 times 5.2 times 1.6 squared, but I'm pretty sure that 8.6 kilogram block is now moving. There's no way that that first mass could bounce off of it without causing that second mass to go in the opposite direction. So I'm also going to have 1/2 times 8.6 times however fast it's moving. This is going to be how I'm going to calculate the kinetic energy loss. I need to find that mystery velocity, and I'm going to find that mystery velocity by analyzing the collision. And I could have started with the collision, but I wanted you to know why I'm starting with the collision. It's because I know that to find the kinetic energy lost, I want all the kinetic energy at the beginning and all the kinetic energy at the end, but I don't know all the kinetic energy at the end because I don't know how fast that second thing is moving. So I'm going to solve for that with a collision. I don't see angles or anything like that, so I'm going to take a couple of shortcuts just so I can try and fit this all on one page. I think what I'm going to call this mass 1, I'm going to call this mass 2, and I think before the collision we have mass 1 V1 initial, and after the collision they are not stuck together. Rebounds means it bounced off. I'm going to have mass 1 V1 final plus mass 2 V2 final. And I would like to find that. And because everything is in a straight line, I don't need to bring out the cosine law, sine law trick. I can just get the V2 by itself. How? Minus and divide. I think I'm going to get this. V2 final is going to be M1 V1 initial minus M1 V1 final divided by mass 2. M1 was 5.2. Yes? It's a little weird. We're so used to having final minus initial. This time I do have initial minus final. Okay. What's the initial velocity of mass 1? Yep. And then I'm going to have minus mass 1 is 5.2. I've changed the number. What's the final velocity of mass 1? And I'm going to cut you off, and I'm going to say the answer is not 1.6. What? Yes! And mass 2 was 8.6. And can you see, Court, I've got a minus, which is a plus. And if I miss that, I'm going to get the wrong, completely the wrong velocity, yeah. In fact, this minus makes it a plus. You actually get a bigger velocity, which does make sense because that first guy coming in, if it bounced off backwards, it transferred a lot of positive forwards momentum to that stationary mass. It should be going pretty fast. 5.2 times 9.4 minus 5.2 times negative 1.6 divided by 8.6. So I've changed the numbers. This will be different from your answer key, but I get 6.6511. 6.651 is probably enough sig figs to carry. That's what I would put there, and then I would carefully crunch the rest. And that would give me the kinetic energy lost. I should get a positive answer. Let's find out. 1/2 times m times 9.4 squared. That's how much I started with. Minus, bracket, 1/2 times m times 1.6 squared. Now, I should call that negative if it was a velocity, but in energy it's a scalar, so I don't care. And also, even if I did, the negative when it got squared would vanish anyhow. It's one of the reasons why kinetic energy is a scalar. Okay? And I also have the 0.5 times 8.6 times, I'm going to go answer button squared. And I've lost 32.9 joules. I'm guessing that's really close to what your answer is because I only changed the velocity by a tiny bit. Okay? That's a nice example of a combined work energy conservation momentum question. I'm not going to give you one with angles. And suddenly I lost everything. Where did it all go? Okay. No. Go ahead. Any others you would like me to go over? Yeah.
Number 3 on lesson 4.
Lesson 4, number 3. Oh, I remember this one. This is very similar to the one we just did in that it's a linear collision and there's a rebound. I'm not wild about B. I've changed the wording for B for next year, but I'll show you what I mean in just a second. I'm not going to solve it completely. I'll just get you started. It wants you to find the average force. Okay, well, I think my first thinking, force, you say? Maybe I'm going to try this. And then I said, okay. And then I got really clever. How much time are we talking about? Oh, so this is going to be a 1. So I'm going to stop writing dividing by t in the next line. It's not that the t canceled. It's just I'm dividing by 1 for Pete's sakes. Okay. What's the mass? Well, it's 3 tennis balls, and each one weighs 70 grams.
Okay, I was just going 70.
There you go. Okay. Now, for B, what I don't like about B is for B, you do have to use only the 70 and not the 3 times 70. So next year I've added absorbed by the wall from each ball, I think, or from each mass to let them know that actually ditch the 3 for part B. And so for part B, you'll go the final kinetic energy, the initial kinetic energy, you 1/2 mv squared initial minus 1/2 mv squared final. That's what you absorbed. That's what you lost. That's what the wall absorbed. Is that okay?
Yeah.
Do you want me to keep going, anybody, or was that enough? Okay, that was easy.
Could you do number 5, please, from the
Same homework?
vector review?
Oh, from the vector review, ultimate review.
Yeah.
Number 5. Sure. I'll just change the numbers a tiny bit. Okay. Here. Now it's a whole new question. Okay. I'm not going to change what it said. Well, okay, fine. I can see some of you change that too. Okay. What's the speed of the main capsule after the explosion? They did say speed, but I think there's an explosion. I think that's a job for conservation of momentum. So I would start out thinking to myself, the sum of all the momentum initial equals the sum of all the momentum final. Before the explosion, what's moving? Both stuck together. So I'm going to have this, and I'm going to cut corners and go a bit quick just so I can fit this all in. I'm going to have the mass of both, which I think is 4,000 when I add it together, times 100 in my new version of this question. Yes? boom, they explode. Afterwards, I'm going to have the 2,500 kilogram times its velocity plus the 1,500 times 140. Now, I notice that the small capsule sped up. It's possible then that this one might actually end up slowing down a little bit. Maybe not, because this has a smaller mass. Maybe there was enough energy to go around that, well, I think this one's going to end up having slowed down. Is this in a nice straight line? Then I can just get the VF by itself. It's going to be this times this minus this divided by 2,500. I'm just going to crunch it because I need it for part B anyhow. So it's going to be bracket 4,000 times 100 minus 1,500 times 140 divided by 2,500. Wow, by a fluke, mine worked out evenly. That's a total fluke. I got 76. VF is going to be all the initial momentum minus the momentum of the probe. Whatever's left is the momentum of the capsule, and if I want to find the velocity, I divide by the mass. Did you also get 76, or did you try it? Okay, that's for the original numbers. Yeah. Okay, but for these numbers. Now, what does part 2 want me to find? What's another word for impulse? Oh, so for the probe is going to be final minus initial of the probe. This one, you know what? It's going to be mass V final minus mass V initial, 120. That's it. Don't overcomplicate it. Oh, now, that's going to be the impulse that the probe got. If you get a positive answer, the probe gained momentum. That's exactly how much momentum the capsule lost, because momentum is conserved. So was there, I think there was a part C follow-up, wasn't there, to this one? And it's probably, define impulse, change in momentum. Why is it equal in magnitude to the impulse on the main capsule? In magnitude, it'd be opposite signs, but because momentum is conserved. Yeah, I mean, really, if you said that, I'd have to give you full. So I'd probably, for 4 marks, impulse is equal to change in momentum. If you wanted to impress me, you could also write which is momentum final minus momentum initial. I would accept it if you then said they're equal because momentum is conserved. If you really wanted to impress me, you could actually solve and show that they were the same, which they are. In other words, part B said find the impulse on the probe. If you also found the impulse on the capsule, you'll get the same answer but negative. You have to. Is that all right? Next? Yeah, Julie. 212? Oh, now we're into the momentum at angles. Number 12. I don't remember 12. Okay. This is a good question. A little ugly and no picture. I would feel okay giving you no picture, maybe on a multiple choice, but not that often. Certainly on the written, you will get a picture. So we'll try this one as is. It'll also be a way to check my answer key to see if I did it right. There's a collision. Wow, model airplanes colliding. What are the odds of that? But okay. I was stealing this from everywhere. There's a collision. This is a job for conservation momentum. Julie, I'll pretend this is a test. I won't take any shortcuts. So I would start out by going the sum of all the initial momentum equals the sum of all the final momentum. I would also, Julie, do this because I've botched that many a time. I'll call this mass 1. I'll call this mass 2. Before the collision, what's moving? Mass 1, mass 2, both or neither? Both. Stuck together or separate? Before the collision? So, ready? Before the collision, what's moving? Mass 1, mass 2, both or neither? I agree, both. Stuck together or separate? Okay. So I'm going to have this. Momentum of mass 1 initial, momentum of mass 2 initial. Wham, they collide and stuck together. Are there angles? I'm not just going to go MV, MV, M and get the V by itself. Are there angles? I'm going to dulp. So it looks like the first plane is traveling to the south, and its momentum is mass times velocity. It's 0.4 times 20. I think that's 8 even. The second one is the tricky one. Can you read to me what I just underlined? Look up. Can you read to me? East of what? East of what? East of what? I'm going to draw south first. Folks, can you keep it down a little tiny bit? Thank you. I'm going to go east of south, 20 degrees. And this vector is going to be mass times velocity 12.5. And then it hasn't told me what they equal. But you know what? I'm okay. They told me the two vectors I'm adding together. How would I add them together? So I'm going to draw a nice big triangle. It's going to look like this. 8. And the 12.5 should be a little longer than the 8. And because I'm adding these together, now if this was an explosion with an initial momentum of 0, I would go back to where I started from. But that's not what this question is. Here, I am adding two vectors together, so it's going to be from the tail of the first to the tip of the second. This is the momentum of both. I got to get an angle. It looks like the angle that they gave me, this one here, is 20 degrees, which is not in my triangle. How big is that angle? That looks like a 90-degree angle to you. Don't 90-degree angles look like a letter L? So how big is that angle? Not 90. Ready? What does this form? A straight line. What does every straight line add to? So if this is 20, how big? By the way, and this is not to make fun of you, your guesses of 70 and 90, I am going to say are bad guesses because that's clearly bigger than 90 degrees. This is why, by the way, I try and tell you, draw them roughly to scale. So if you draw your triangle roughly to scale, hopefully you would say, and this is not meant to denigrate you, 70 is a bad guess, right? 90 is this, 70 is this, bigger than 90, it's got to be bigger than 90. You get what I mean there, yeah? So this is 160 degrees. And now we're into cosine law land. How do I know? No pair, and I also have spotted very often two sides and the angle between them. I'm finding what's across from it. That's cosine law. So I'm going to get momentum both squared equals 8 squared. Folks, you be a little quieter? Thank you. 12.5 squared minus 2 times 8 times 12.5 cos 160, and then square root. 8 squared plus 12.5 squared minus 2 times 8 times 12.5 cos 160. Square root. The final momentum of both is 20.20367. I'll write all those because I'm going to use this. And there's a 0 after the 6th. That seems like a nice place to round off to still be accurate. I'm probably carrying too many sig figs, but I'll be paranoid. Momentum of both is, what did I say? 20.20367. 20.20367. How can I turn this into a velocity if I know the momentum? And by the mass of both this time, because they're stuck together. Were the masses 0.4 and 0.5? Okay, so I'm going to divide by 0.9. There's my speed, 22.84. Sorry, 22.44. 22.4 meters per second. Now I need a direction. Well, no, that's not a direction. I need a theta. Ready? The theta does not go here where it's pointing. It always goes where it's coming from. The theta is going to go here. And this is actually a nice theta because it is next to a vertical or horizontal line, a vertical line in this case. And it is going to be start out going south and go east of south. I agree it is going to be east of south, but I need to find the magnitude. If you just say east of south, that's not the direction. I need the actual degrees. Sine law. Why does sine law work? Because now I have a pair. I know the 160 and I know the momentum of both, so I can use the sine law. You could, if you wanted to do this using the cosine law, but sine law is a little quicker. I'm going to have this, the sine of the mystery angle over what's across from it, which is 12.5, is the sine of the angle that I know over what's across from it, which is 20.20367. To get the sine theta by itself, I'm going to times the 12.5 over. I'll divide by the 20.20367. That's the sine of theta. And now I go shift sine, answer button, and I get 12 degrees. Is that okay, Julie? Now, for all of you, you might recall we did talk about an ambiguous case for the sine law. I showed you that because I'm a nerd. On the test, I'm very careful to keep all of my collisions at small enough angles that it'll never be an issue. Just because. Sinead.
Number 13, I just don't really-
From the review?
Yeah. I don't really get how you got the equation that you put in the answer key.
Let's go look at my answer key that shows all my steps for number 13. Number 13. One too far. Oh, the O'Dwyer maneuver. The one that your sister found. So I used to do this really long. And then your sister said this, okay? It wants the magnitude of the impulse. It wants the change in momentum. She said, Mr. Dewick, since the x velocity, the horizontal velocity is constant, there is going to be no change in momentum horizontally. She said, although this says find the impulse and it hits at an angle, all you need to do is find the vertical change in momentum because that's all there is. And I went, oh, I never thought of it. I had actually found all the velocities, all the components. I had added them together, tip to tail, and done a whole bunch of trig. And then she said, no, Mr. T, you don't need to do that. So that's why I wrote, since Vx is constant, there is no horizontal change in momentum. So I'm going to use force change in time. This was your sister's suggestion, equals impulse. What's the force? You know what? It's mg, because it's falling in free fall. What's the change in time? Okay, I calculated the change in time. Oh, they told me the change in time. Good, that's it. Because horizontally nothing is changing, so all I'm finding is the vertical change in momentum, and I know the vertical force, it's mg.
Will there be questions
Like this? Probably not. It's a nice thought question because it looks really ugly, and I did it really ugly, and then someone clever showed me the O'Dwyer maneuver. I think I spelled maneuver wrong, though. Is maneuver UE and not EU? I might have to fix that later. Can't remember. Can I do which one? 44? Sure. I added this question this year. You guys are the first group to have it. Because I wanted to try and find an example of a graphy question. So I came across this. First of all, I found the area, and you can see I broke it up into a triangle, a rectangle, and a triangle. Are you okay with that part? And I got an impulse of 2 kilograms. Nice answer. Great, 2. Now, they want the final momentum. I said, well, what's another word for impulse? Change in momentum. So this 2 is final momentum minus initial momentum. So I said, oh, it's also east. I looked at the directions that they were talking about. They did say it was traveling east, and I got a positive answer because I figured I might need a directionally thing. So I'm going to let east be positive, west be negative. How would I get the final momentum by itself? Okay? And this was the key. The initial momentum was west. And that's why there's a negative there. Then it was plug and chug. Soon as they start sticking directions in, my antenna always goes up, especially if it's a linear question. Why would they have given me the direction if it's a linear question unless there was going to be a change in direction somewhere along the way? Is that all right?
Yes.
Any others? This is your chance. Okay, let me pause things for just a second. We're going to pause the video. Number 6, I like number 6, I like number 6. Although for number 6, I would also then like to find how high they go up the next hill. Okay? Yo. Thank you. This one. Oh, you know what? I lost some writing again. This happens sometimes. I'm not quite sure why. This one here. Now this would be easier if I'd given you a picture. This might be a time for me to draw one of my world famous artistic diagrams. Actually, really, you could almost use this picture here. We'll just change the numbers and ignore the drop off. But this is really what's happening in number 6. I think in number 6 what I have is a mass coming down a hill and colliding with another mass. Am I not right, I think? Yeah. Oh, it's even a 2 kilogram mass. That works. It's a 5 meter high hill, and it hits a 3 kilogram stationary mass, and they stick together. Okay. The most common mistake kids right away start going into trying to solve this with momentum. The collision is the second part. The first part is the hill. Change in height, change in speed, curvy path. I think here, 0 and 0. So I'm going to get mgh initial equals a half mv final squared. M cancels. Yay! I think the speed at the bottom of the hill is going to be 2 times g times h initial square root. It's going to be 2 times g times h initial square root. I guess 9.9. You know what? I'll carry some extra. I'll go 9.8995. I'll round to there, and that way I got enough room to. Okay. So 9.8995. Let's make sure I didn't make a typo. That answer looks weird to me. Did I miss a squared or anything like? No, it's 2 times g times h, and then square. Okay, square root of 98. Yeah, it'd be 7 times root 2. That works. Now there's a collision. I'm just going to skip steps, but I think before the collision we have mass 1, v1 initial. Wham, they collide and stick together. So v final is going to be mass 1, v1 initial divided by the mass of both. It's going to be 2 times 9.8995 divided by 5. There's the 3.96. I think on your test what I would now say is there's a hill. How high will they go up the next hill? And again, you would go conservation of energy, but this time you'd be finding H final. V final would be 0. Is that all right? Probably. Oh, I can't imagine you ever complicating things. Oh. that slipped out. I taught her for 4 straight all the time. Next. Well, the tone's going to go in a couple, so I'm going to pause the video